Okay, folks, welcome back to KDD2, week 3. We are in the middle of lecture 2, and just a very short recap what we've seen before in the lecture. So we talked about feature spaces in general. That was this one here. And then we talked about challenges of high-dimensional data, why we should care at all about high-dimensional data. So we had this very funny baby shape game before, where we discovered that if we have a lot of features that may reflect different semantic concepts, different semantic layers, we may also end up in different concepts, different patterns in the data, of course. Yeah? And of course, the probability that we have such scenarios increase with increasing dimensionality of the data space. So yeah, we talked about that high-dimensional data is existing actually. We talked about several problems that somehow limit our methods. So the distance concentration stuff, that distances become larger, of course, but also tend to concentrate with a bad impact on the concept of neighborhood, where we talked about unstable neighborhoods. So basically, in high-dimensional cases or high-dimensional spaces, it is usually the case that your next neighbor is a kind of random object, and the distance to the next neighbor and the distance to the farthest neighbor is more or less the same. That is this theorem here. Yeah? Yeah, we talked also about the growing data space having impact on the hypothesis space, of course. So we need much more samples to test hypotheses, to make models more stable. So this is this one here. And we also had the problem that with the growing space, a lot of areas in that data space are empty, and the tails of the distributions get more and more important. So this was the point, that the data concentrates typically on the border, statistically on the border of the data space. Yeah? So the probability that we have some points within this range here decreases extremely quickly. So the probability that the points just gather around at the borders of the data space is very high in high-dimensional spaces. That means that this traditional Gaussian curve does not hold anymore in high-dimensional spaces, but we will see a lot of things down here at the tails of the original Gaussian distribution. Yeah? That was this observation here. There are some further problems. We didn't go into details too much here, but we had to discuss that beyond all those problems, or the basis of all those problems, are some specific assumptions that need not necessarily hold. Yeah? But the main assumption was that we assume that all attributes, or most of the attributes, are irrelevant to the data mining task, yeah? Or correlated with each other, so that they somehow over emphasize, or they are overemphasized. Yeah? But typically we assume that that attributes are independent and uniformly distributed, and in this case they are completely irrelevant to the data mining task. And in that case we typically have a curse. There is the other way around. We talked about that for example, if we use a special kernel, it may be a blessing to pump up the feature space. Yeah? A kernel typically pumps up the feature space, so in that case it's a blessing. Yeah? So that was the case, Krüger versus Tress. So now what we do this week is we look at supervised feature selection. So this week will be chapter 3 or section 3 in this chapter 3 on high dimension, or lecture 2 on high dimensional data, sorry. And we will talk about if we are in a supervised selection scenario. So keep that in mind. We will be in a supervised scenario now, and we will try to find the relevant features. And before we talk about methods to do that, so this is a pre-processing step. Yeah, that is mostly. Sometimes it's part of the data mining, but very often it's part of the preprocessing step. But before we talk about how to do that, we'll talk about what we actually want to do. Yeah, we recall we want to, or the curse comes from irrelevant and redundant features, and obviously now we want to remove those features, irrelevant attributes, irrelevant features, because they are not useful for a given task, and probably decrease the accuracy, because we run in all those problems of we talked about just before and last week, the curse of dimensionality. And also redundant features, we mentioned them already, because if we have strongly correlated features, then those features may overestimate the patterns they have, if they have patterns, or if they don't have patterns, they may overestimate noise. So anyway, the redundant features introduce a bias that is maybe wanted, but very often not wanted. Yeah. So in this case, redundant features typically do not drop the accuracy. They may drop efficiency, of course. They may drop explainability, but they may also introduce a bias. And you also always have to think of, do I really want to have this bias? I mean, it could be interesting to not delete redundant features, because you want to have that bias, of course. Yeah? You want to have the bias towards specific patterns. But anyway, so yeah, deleting irrelevant, especially irrelevant, but also redundant features can improve the quality. Yeah, of course. And also it could improve the efficiency, because we have less features, and also it could improve the accuracy of the found patterns. Yeah. So what we do in feature selection, so please be not confused with all those different terms here. There are in the literature, people talk about feature selection, dimensionality reduction, and feature extraction, and they mean typically. It's not a perfect consistent literature here and perfect consistent terminology. That's a pity, because it can be quite confusing. So don't get confused. In this case, feature selection means that our new feature space just deletes all useless features from the original space. So the feature selection is a kind of dimensionality reduction, but people usually don't use this term dimensionality reduction for just this one here, where you just delete some features. Yeah. So feature selection keeps the original features, but just removes some of them. In dimensionality reduction, when people talk about dimensionality reduction, they typically assume that they also somehow derive new features from the original feature ones, from the original ones. Yeah. So in dimensionality reduction, that's the difference to feature selection. The old original features are not kept, but we derive new and less features actually. Yeah. And feature extraction is again a different thing. We will talk about that in the next weeks. So keep that in mind. Feature selection just keeps the old features but tries to get rid of some of them. Yeah, so it's a kind of dimensionality reduction. That's why it's confusing. It's a dimensionality reduction, but it keeps the original features. Yeah, so that is how the community use these or this term actually. So let's talk about what we want to get rid of. So we want to get rid of irrelevant features and redundant features. So here is an example. Look at the two-dimensional space first. We have two clear patterns, one here, one here. And if you have a look on the projections, so the individual features, you see that here the Y feature does not really have an impact to, or does not reveal any you cannot distinguish the patterns we have in the two-dimensional case just by looking at Y. Yeah, so Y is irrelevant to distinguish those two patterns, whereas X is, because you need X to actually distinguish these two patterns. Yeah, so in that case, Y would be irrelevant and X would be relevant. So we would like to get rid of of Y and keep only X. Here is redundancy. So here again you see in the two-dimensional case two patterns, two clear patterns you may want to distinguish. In a supervised setting you want to learn a model how to distinguish them. In clustering you may come up with two clusters. So in that case you see that both actually are good, both one-dimensional projections are good to distinguish those two patterns. Yeah, X is good here, and here you have these two patterns. Y is also quite okay. It's not that good as, probably as good as X, but it's absolutely okay. So in that case, those two are somehow redundant. We would only need one of them to really distinguish those two. Yeah? So in that case, we could get rid of one of those two one-dimensional features and just keep, for example, X again and get rid of Y. But we could also keep Y and get rid of X, of course. So this may suggest here, the irrelevance case may suggest that the features that have a high variance are better than those that have a low variance, but that can be completely wrong. We will see some, so that's why we talk about that here with a counterexample. We will explore some methods that assume that the directions of high variance are more important than those along small variance. For example, PCA in the dimensionality in the dimensionality reduction later on, and that can be completely wrong, as you see here. So in this case, the direction with the high variance does not reveal anything. That is the x-axis here, but the y-axis has a very low variation, very low variance. But in this example, y is the one we should keep, yeah, because in y we can really distinguish those two. Okay, so irrelevancy need not to be let's say correlated or related to variance. Yeah, keep that in mind. And here are some other very nasty things that can happen. So just that you see, it's not the real world is not looking so easy as it looks here, but it can be really nasty. So this is a nasty example, and this is also a nasty example. So both things are perfectly correlated, like here. They are also perfectly correlated, x and y. But you cannot really distinguish which one to keep, yeah, because both features are redundant, obviously, but both features are not really good in just distinguishing the green ones from the red ones. So that is more like it looks in reality. So in this case, it's hard to judge, or just feature selection may not really work, because if you keep x, 1 in that case, the x-axis here, or if you keep y, x2 here, named x2 here, doesn't make a big improvement. Yeah? Anyway. And here is a very interesting example that should somehow warn you. So just looking at two-dimensional examples could be a little bit misleading, because in high-dimensional cases, if you have a lot of features, a lot of things can happen actually, and you see just a taste of what can happen even in 2 dimensions. Here you have 2 one-dimensional features that are completely irrelevant. You see, if you take x2 here, this feature here along the y-axis, you cannot distinguish the reds from the greens, right? And the same holds true for this x1 feature along the x-axis. But if you combine them, you may have a chance. For example, if you use a random forest, a decision tree here, a decision tree may have the chance to really distinguish between those 2 classes. Yeah, it's just because you combine 2 individually irrelevant attributes, and you get all of a sudden a relevant attribute or a relevant subspace. And those things may happen as you increase the dimensionality. So keep that in mind when we discuss now different things. Because anything can happen, and nobody has a real good intuition, as we saw in the previous section on the curse of dimensionality. Strange things happen in high dimensional spaces, and our intuition usually fails to really explain them. So keep that in mind.